Hello students, our next topic is AC voltage applied to a series LCR circuit. Now individually we did AC voltage applied to resistor, then AC voltage applied to inductor and AC voltage applied to capacitor, where we found the phase difference between the voltage and current. In a resistor circuit, the phase difference between the voltage and current was 0. In an inductive circuit, the current lags behind the voltage by pi by 2 or 1/4 of the time interval or the total periodic time. And in the capacitor, the current leads the voltage by pi by 2. Now we have a series combination of LCR circuit. So let us consider a series combination where a resistor of resistance R, an inductor of inductance L and a capacitor of capacitance C is connected in series with an AC source V is equal to Vm sin omega t. That is our instantaneous voltage. Let the current at any instant in the circuit is I of t, that is an instantaneous current. Now see, in the DC source, suppose the DC voltage or the terminal potential difference of a battery is 20 volt, then the sum of all the potential difference comes out to be 20 volt. But it is not the case with the AC circuit because there is a phase difference between the current and the voltage. So individually we know the phase difference between V and I. Now LCR is connected in series. So suppose in a DC source we have two identical resistors which are connected to a battery of 10 volt. Then the potential difference across this R is 5 volt and across this R is 5 volt. That is, I mean to say, the sum of the potential difference across the component is equal to the total sum of the supply. But here, if our VRMS is 220 volt, then the voltage across R, L and C would not be an algebraic summation, because we know that the voltage and current phase relationship is different for individual components. So it will not be the case in this. So what should be the, if our VRMS is 220 volt, what is the potential drop across R, L and C? But you will see the total will not be equal to 220. We have some another relation. Now the voltage drop, instantaneous voltage drop across R is, say, VR, small VR, this is VL and VC. But the phase relationship between the current and the voltage is different. Now it should be clear from the diagram that current in this situation, in all the three components, R, L and C are referred as a components here. The current through each component is same, but the voltage will not be same. So we have to find out the solution of this equation. So let us consider first the general description of this equation. So let a resistor of resistance capital R, inductor of an inductance L and a capacitor of capacitance C is connected in series with AC source V is equal to Vm sin of omega t. That is our equation 1. Let I of t be the current in the circuit at any instant. Now the voltage equation here can be written as V is equal to VR plus VL plus VC. Therefore, V is equal to IR plus L di by dt plus Q by C. So this is our voltage equation. Individually we have written this equation. So the potential drop across resistance is IR, across L it is L di by dt, and across C it is Q by C. So this is the instantaneous voltages across R, L and C. Now we have to solve this equation, or you can say we have to find out the solution of this equation. So there are two methods to find out the solution of equation. Here the solution means I have to find out the value of I in for this circuit. So now this current in the circuit will be same, having the same amplitude, but now current will not lead or lag by 90 degree. So individually, if I have inductor, the current will lag the voltage. If a capacitor, the current will lead the voltage. In a resistor, they are in same phase, but now the current is different. I mean to say the phase difference between V and I will not be now 90 degree. So neither it will be 0 degree or 90 degree. There should be some other value that we have to find out. So finding the solution means I have to find out the equation of I in such a way that if I substitute this value I here, do the derivative of I, and in the place of Q I can write the integration of I with respect to time, that is I dt, and if I substitute that I equation, then it satisfies this equation, that is LHS is equal to RHS. This V is Vm sin omega t. Now there are two methods to find out the solution of this equation number 2. One is a phasor method and one is analytical method, that is purely a mathematical concept. And phasor diagram, we know it is a graphical method, and the phasor diagram is easier as compared to the analytical method. So we will find out the solution of this equation 2 with the help of a phasor diagram. Now to draw the phasor diagram, we have to represent a phasor. So let this VR, VL, VC and capital V be the phasor of resistor, inductor, capacitor and source. We know what is phasor. Phasor is a vector which rotates with the angular frequency in anti-clockwise direction or counter-clockwise direction. And for a source, when this phasor rotates, it gives a graph of sine. So now we consider this as a phasor of the respective components to draw the phasor diagram. Now how will the phasor diagram be drawn for the components? So if you have a series LCR, you may also have a parallel LCR. If you have a series LCR, while drawing the phasor diagram, first thing is we draw a phasor which have the same quantity. That is, I mean to say, in LCR circuit or whenever any components are connected in series, the current through each of them is same. So in this, the current in each component is same, the amplitude is same, and the instantaneous value will also remain same. So the current in each component is same. Here, current in each component is same. So first we have to draw the phasor of a current which is same. So if you have a parallel combination, we know in a parallel combination the potential difference across each component is same. So in that situation we have to take a phasor IR, IL, IC and capital I, that is you can say a resultant current, so or a equivalent voltage like this. So here because we have a same current, so there will be only one phasor of current. And if you have a parallel combination, the current would be different and potential difference will be same. So let us assume the current in each component is same. So let us say the current value here I is equal to Im sine of omega t plus phi. That is equation number 3. Now we know that if we have a resistor only, then I was equal to Im sine omega t. If you have an inductor, we have Im sine omega t minus pi by 2. And if we have a capacitor, it was plus pi by 2. That is current lagging leading. We know that equation. Now here there will be some new equation. We don't know what is the phase difference between V and I. Whether the current in such circuit will lead or lag, we don't know. So here where phi is phase difference between V, that is instantaneous voltage, and instantaneous current. So we will also find out the formula for this phase difference. Also we will find out what should be the value of Im. If you remember the value for Im in the case of the resistor circuit was the Ohm's law, that is I is equal to Vm upon R. Similarly, Im was equal to Vm upon XL. For inductor, Im is equal to Vm upon Xc. So here Im will be different, that we have to find out. Now let us draw a phasor diagram. Try to understand how the phasor diagram is drawn. So first we draw a phasor of a quantity which is same in the circuit. So here it is a series combination. So we will find out, first we will draw the phasor of I. We will draw the phasor of I. So let us draw the phasor of I. So this is capital I. Now this current in the entire circuit is same. So the amplitude, that is the peak value Im for each component, will be same. Phase difference will be the resultant phase difference. So I is same. Now let us draw the individual phasor from the previous knowledge. So VR. So VR is in phase with current I. So we draw again a phasor VR on the same line as the phasor I. So clearly the phase difference is different. The phase difference is 0. So the VR phasor and I phasor are parallel to each other, or the angle between them is 0. We know this angle we have drawn, it should be this, that is omega t plus phi. Because it's vertical component, we know the vertical component always give us the sine component. Now for L we know current lags behind. It means the voltage VL will lead the current by 90 degree. Current was lagging by 90 degree. So in other words, I can say the voltage will lead the current. So I draw a phasor of VL, that is 90 degree. So exactly this should look like a 90 degree. This is the phasor of VL. So this is phasor of VL. So clearly the voltage is leading the current by 90 degree. For C, the voltage current leads, so voltage should lag behind the voltage. So with respect to current, the voltage should lag behind. So this is a phasor of C. Again, this angle should be 90 degree. Here we have drawn the length of phasor VC, that is its amplitude is more than the inductor. It means the circuit is capacitive. The circuit is capacitive, that is C dominates the circuit as compared to L, or you can say C की दादागिरी ज़्यादा है as compared to L. So circuit is capacitive. In other words, we can say for such diagram that XC is greater than XL. If it is given that XL is greater than XC, so we draw the magnitude or the length of this phasor more than the phasor of C. Now we know phasor is a vector, so we consider this 3 to be a vector. It is like you have to do the addition of 3 vector quantities having different directions. So at a time we can add 2 vectors using the triangle of vector addition. Now both these vectors, so though they are not vectors and therefore we name them phasor, but to explain you I am calling this 2 as a vector. So clearly this vector is greater than this and the angle between them is 180 degree. So we will subtract the magnitude of this vector from this vector. That is, if I say this is 5 Newton force and this is 3 Newton force, so resultant will be 2 Newton in this direction. So first we will do the addition of this and then the resultant of VC and VL is added to VR, and finally we will find out the resultant vector. So it is like a addition of the 3 vectors. We will do the addition of the 3 vectors. So in the terms of the magnitudes, now let us see the theory. We know that Vm is equal to IMR. So Vm can be written as IMR. Again, the Vm can also be written as IMXCXL, that is the Ohm's law, that is the maximum value of the voltage across the resistor, inductor and capacitor. It will be different. Why it will be different? Because V and I differ. There is a phase difference. So we put a symbol VRM, that is the amplitude of the voltage across R. Similarly, we introduce the symbol VLM as IMXL, then VCM, that is equal to IMXC. You see the current in each component is same. The magnitude, the amplitude or the peak value of current in all is same. So all the 3 components will have same current, same phase difference with respect to the voltage, because their voltage differs. See, this phasor I is same for all 3 components. We have taken this I as a reference. If you have a parallel combination of LCR, then first we will draw this capital V, and respectively we will draw IR, IL and IC. If it is a parallel combination, this is a series combination. Now we will draw the relation of their amplitudes. We will draw the relation of their amplitudes or the peak relation or the peak values. So in the vector form also, this is a vector form diagram, or you can say it is a phasor diagram. Now let us do the addition of these 2 quantities. So we have taken XC greater than XL. So in the terms of vector, if I add these 2 vector in the vector form, I will write this as VC plus VL. That is a vector notation. It means we did vector addition. Here plus sign, it is not like, we know that A vector plus B vector is equal to R vector. Now if I say the magnitude of A vector is 2 meter and the magnitude of B vector is 3 meter and they have a different direction, so answer should not be the 5 meter. It should be under root A square plus B square plus 2AB cos theta, angle between them. Here this is only the symbol that we did the vector addition, and because VC was greater than VL, the resultant is in this direction. So let us say this is 5 Newton example, this is 2 Newton, so resultant should be 3 Newton. Now what will be its magnitude? So if the magnitude of this is represented by Vm, so VLM. The magnitude of this is VCM. Individually we did the phasor diagram. So the resultant magnitude of this should be equal to VCM minus VLM. That is 5 Newton minus 3 Newton. So answer should be 2 Newton. So the length is drawn accordingly. The magnitude of this vector, that is VR. So this is VR. Again this is angle is 90 degree and its magnitude we know is represented by VRM. This angle is omega t plus phi. So from the three vectors, though they are not vectors, they are the phasor. So from the three phasors, VR, VL and VC, we combine the VC and VL into a single phasor. So now you are left with two phasors, VC plus VL and VR, and we have written their magnitudes. So the voltage equation, this is called as a voltage equation. So voltage equation is V is equal to VR plus VL plus VC. Say equation number 4. Phasor equation. So capital VR plus VL plus VC is equal to V. This is the phasor equation. It is like R vector is equal to A vector plus B vector plus C vector. Like this. This is a vector equation. But we cannot put an arrow on them, so we name them as a phasor. So first we combine B and C, that is VL and VC, into a single phasor. Now there will be addition of this. Now we know that if we have a two vectors having this angle 90 degree, then the resultant should be somewhere between it. So let the resultant phasor is V. This is the resultant phasor, that is resultant vector. Now angle between B and C was 180 degree. So the magnitude is VCM minus VLM, minus sign because XC is assumed to be greater than XI. Then addition of this is done to this A vector. Now angle between this two, this combined vector, let us name this combined vector as B dash vector. Now what will be angle between A and B dash? Clearly the angle between VR and VC plus VL is 90 degree. So the magnitude is under root A square plus, in this situation, A square plus B dash square plus 2AB cos 90. Cos 90 is 0. Else, you can see that I take this vector from this side and without changing the direction, I put this vector here. I put this vector here. So this vector magnitude is VCM minus VLN. So this angle is 90 degree. So now you have a right angle triangle. We have a right angle triangle. The angle between the magnitude of VCM minus VLM and VRM is 90 degree. Now you can apply the Pythagoras theorem to find out the voltage relation. So this is a voltage equation, that is instantaneous voltage. This is a phasor. Now I need to find out the magnitude. So I apply the Pythagoras theorem here, or I can redraw this diagram at this point. This is 90 degree. So we have this as VR. Then we have this as let us write the magnitude VRM. This is VCM minus VLM, and this magnitude, that is joining the tail to the head, that is the resultant Vm. So we have to apply now the Pythagoras theorem. So it is like the vector addition, where the two vectors are added. So this is your base height and this is your hypotenuse. So we form a right angle triangle. And now this angle, what is this angle? This is phi. That is the phase difference between the resultant vector and the r vector. So if here it should be, this angle is phi. That is the phase difference. So when you find a resultant, if you remember, the formula for the resultant tan alpha was written as b sin theta upon a plus b cos theta. So where alpha was the angle between the resultant vector and a vector. So that is the vector concept. So here what is phi? Phi will give you the phase difference or angle between the resultant vector, this is our resultant, and VR vector. Also, the current is in the same direction. The current is in the same direction. So if I want to extend this, this is also a current also. So I can say phi is the phase difference between V and I. So if I say this as Vm, it should be Im. So phi is the, you can say phi is a resultant phase difference, which was 90 in individual cases, 0 in our case. Now there will be some different value. So we have to apply the Pythagoras theorem here to find out the resultant vector. So you see that these two vectors VRM and VCM minus VLM are in the same order. So resultant is in the opposite order. These are in the same order. So we take this VRM, then VCM minus VLM, then your resultant vector is in the opposite order, that is phi, and this angle is 90. Now these are two identical triangles drawn separately to understand it. So clearly this is the vector equation. Now I have to write the magnitude. So I apply the Pythagoras theorem. So applying Pythagoras theorem, Vm square is equal to Vrm square plus Vcm minus Vlm square. So see, this is the relation. So if your Vm is, for example, if your Vm is 220 volt, then Vrm plus Vlm plus Vcm will not be equal to 220 volt. we have found that if Vrms is 220 volt, the maximum voltage was 311 volt. If Vrms is 220 volt, the maximum voltage was 311 volt. So if our supply has the maximum value of 300 volt, then the resultant of this Vrm, Vlm, Vcm will not be equal to 311 volt, but the square of 311 volt will be equal to the square of this individual maximum value. So this is the equation for the resultant. You can say this is the resultant peak value of AC supply, and that we have obtained from the vector addition, that is vector A. So vector A plus vector B. So resultant is taken in the opposite order. So this is how we find out the peak value of the voltage for series LCR circuit. Now, once we know the formula for Vm, so if you have all three are connected in series, and if you are required to find out the maximum voltage of the supply, so it should be Vrm square plus Vcm minus Vlm square. Now we have to find out what is this phase difference. But before that, we will also find out Im. So we apply the Ohm's law here. Individually we substitute all these values. So Vm square is equal to, so in the place of Vrm, I put Im square R plus Im Xc minus Im XL whole square. So we substitute this individual peak values in this equation number 6. Therefore, Vm square is equal to Im square is here it should be R square is taken common. So from this Im we have a square, it is taken R, so X square plus Xc minus XL whole square. Again you have to remember we are assuming Xc is greater than XL, that is circuit is capacitive. So therefore Im square is equal to Vm square upon R square plus Xc minus XL whole square. So individually if you remember, in this circuit Im was equal to Vm upon R. There we were not using this subscript R, L and C because we have only one component. So Im was equal to Vm upon R. Here Im was equal to Vm upon XL. Im is equal to Vm upon Xc. But now see the resultant Im. So this can be written as Im is equal to Vm, Ohm's law, R square plus Xc minus XL, Xc minus XL whole square, and we put a under root here. So taking the square root on both sides. So this is the most important equation, and because it resembles with the Ohm's law, so in this we name or we introduce a new physical quantity, and this new physical quantity is nothing but it should be the resistance. It should be the resistance, or you can say it is the resultant resistance. It is the resultant resistance. This was individual resistance, XL, inductive reactance, that is resistance offered by inductor to flow of AC current, resistance offered by capacitor to flow of AC current was capacitive reactance. So you can say this equation as a resultant or equivalent resistance of this LCR circuit. This is equivalent maximum value of LCR circuit. This is equivalent current, maximum current in the circuit. Now this is represented by a symbol Z, and here it is named as impedance. The total resistance offered by LCR circuit to the flow of AC current is called its impedance. So we write this definition. It is the total resistance offered by LCR series circuit to the flow of AC current is called its impedance. So impedance is nothing but a total resistance offered by LCR series circuit to the flow of AC current is called its impedance. So this is the value of Im in LCR series circuit. In the next lecture, we will find out what is this phase difference. So impedance is a total resistance, so its SI unit will remain same, that is ohm. So this is how we find out the solution of the LCR series circuit. So we wind up our lecture. We will revise what we have written. This is the current having same amplitude for individual components. So because they are in a series combination, so current is same. Phi is the phase difference between V and I, which will not be 0 or 90 degree because individually current lags or lead in the case of VL, VC or VR. Then we draw a phasor diagram taking I to be a reference because it is same for all three components. We draw VR on this line, phasor. This is a phasor diagram. The phase difference between VR and I is 0. The phase difference between VL and I is 90. That is voltage is leading, current is lagging. Here capacitor, current is leading, or you can say the voltage is lagging. Both were having the phase difference of 90 with respect to this I. So now we are assuming VC is greater than VL, we do the addition of these two phasor. So in vector form it is written as VC plus VL in the terms of amplitude. This is, we know this is called as a maximum value. So this is VCM. This is VLM. And the amplitude of this is VRM. That is the peak value, constant value. They are the constant value. So we draw a magnitude. We take, first we do the addition of these two vectors. Then this is added with VR. So this is a vector equation. So we cannot put an arrow. Otherwise it is A vector plus B vector plus C vector is equal to R vector. Now to find out the resultant vector, we draw a equivalent diagram in the terms of the magnitude. So this is the relation between VRM, VLM and VCM. So we pick up this vector, put it here. So it is like vector A, vector B. So resultant is the opposite side. So it form a right angle triangle. We apply the Pythagoras theorem. So you can say this is the equivalent VM of LCR circuit. Then we, individually this is an Ohm's law. We substitute value, we find out Im. So you can say it is the maximum current in the circuit, where this is the equivalent resistance, which is named as impedance. So in the next lecture we will also find out whether the current lags or lead and by how much radian or degree. Individually the case, again I am saying, individually the phase difference was 0, current was lagging, current was leading by 90 degree, but now phi will not be, neither it will be 0 nor it will be 90, some new value. So if it is some new value, what should be its formula? That we will continue in the next lecture. Have a nice day.